just go down that road and all that would be ridiculous.
Okay, making holes in CAD, and we've done a few holes, but we have different types of holes. We have simple holes that can be through or blind. A through hole obviously goes all the way through, or if it's blind, it's going to have a depth that is specified. Okay, and then there's three simple types of holes. We can have a hole that is counter bore, which is a flat bottom hole, and you can see also partly the way our Trammel toy is designed. We're going to get a little bit of practice with the hole notes and measuring because you have some hand head screws that are, and you have some countersink flathead screws. So then we have a countersink where that screw head is angled. There are two sizes of countersink screws. 82 degrees is the more common for a flathead, and 100 degrees is a little bit less common. Okay, so we have 82 degrees, but they can be a counter bore, as we see from the section view, is flat bottom. Countersink has an angled screw head. Both of those allow the screw to get below the surface so that it doesn't stick out. Okay, so we see that all the time, right? If we scroll down a little bit, we see our basic hole notes, and again, we've worked with some of these throughout the year, mostly in other projects, mostly just through holes, although we did have some threaded holes as well. We mostly have had simple holes. I think we drilled a counter bore on the stack. Yeah, I think we drilled a counter bore once on the stack, and we had some threaded ones before. So a diameter symbol is the same as for circles. We have this little arrow with a line that's our depth. Countersink, of course, looks like a sink, and that V shape looks like that's how a sink drain is made. It has to go to a low spot and drain down so that the sink will drain. So that's where that comes from, and counter bore is flat bottom. Okay, so if we look at a couple examples that they give us, what do we have here? If we look at the overall diameter is the overall diameter of the screw. Okay, so the screw, or whatever the hole size we are looking at, here, let's do this with colors. Okay, so that's the 0.375 diameter, right? And then we have an overall depth, which is 2 inches, which of course is this depth here. Okay, so then the second part, the counterbore part, always goes on the second line. Okay, so then in the second line on the hole note, we see a counterbore diameter of 0.75 inches, which we see, of course, as this dimension here. And it has a depth of 1/2 inch, which of course we see here. Okay, does that make sense? So again, it's not too hard, but we don't have a lot of practice with them, and not, it'd be boring just to write hole notes if it didn't have a purpose anyways. So that's the hole note and how we write it and how it goes into a CAD program. Countersink works in a slightly different way. Okay, with countersink, you still start with the overall depth and diameter. So we still have the overall depth and diameter of the hole, right? Okay, so that part is the same. What is different is your countersink diameter. There is no countersink depth because it's going to be determined by the angle. So all you're going to give is an overall diameter, and then the angle determines how deep it is, because it's going to drill deep enough to hit that diameter, and hopefully it's enough to be flush below the surface. Okay, questions on that? Okay, does that make sense? Kind of. Thread notes on our train. We had a 1/4-20 screw that we used, so we drilled a 1/4-20 hole in our train body so that we had a place to thread that. So anytime now you start seeing thread notes, anytime you start seeing the notes if it is a 1/4 inch or smaller. Okay, with thread notes, you will see that dimension with a fraction. Okay, once you get below 1/4 inch, and you kind of see this in there, you can have a size 0, size 2. They usually go by 2s, but you can find a size 5 screw. They go by numbers. 6. Usually you don't see 7s, 10s, 12s, and 14s. I think once you get up to 14 might even be a 1/4 inch diameter. So that might be where that numbering system kind of comes from. But you will see a screw designation with a number if it's smaller than a 1/4 inch. If it's bigger than a 1/4 inch, what we see here is the fraction. So this is a 5/16 diameter. And what this tells us, of course, is how many threads per inch. Okay, so that means if that has 18 threads per inch, then if I'm driving that screw, I have to turn my screwdriver 18 times for the screw to go down 1 inch. There's 18 threads per inch. On our train, we had a 1/4 20. Okay, does that make sense? So when you see numbers in front of a screw note, that means it's a smaller screw. When you see the fraction, that means that it's a larger diameter. Okay? And then there are, this is an example. UNC is coarse threads. UNF is fine threads. Okay? So I don't know what the fine thread would be for a 5/16. I know 1/4 20, you can have a 28 or 32 threads per inch if it's fine threads. Coarse threads are the most common, and that's what we have with our hardware for the Trammel. Okay? You will see thread notes on end of course exam. Metric notes are different. What they give you for metric, they give you the major diameter, and then they give you a pitch as a ratio. We don't use a lot of metric threads, and usually what I have to do, if you need one, is you take the screw you have to the hardware store and you try it in a nut and make sure you get it to fit. Right? Anybody ever gone through that experience? 2 people. So metric threads are a little harder to recognize. I can usually, I've worked with enough standard threads, I can look at a screw and say, hey, what size is it and what's the thread count? Every once in a while you'll find parts that are fine threads. Fine threads have a little bit more gripping power, and you often see fine threads on small parts like assembling computer pieces and so on inside your box. So you'll often see fine threads there, and there will be different pitches for the same, but they're just identified with a multiple. I know once I bought a big screen TV, got it open, and I was missing screws to put the base on the television. After you had the TV unboxed, you're going to drag it back to the store. No, I just went to the hardware store and figured out what size I needed. So, right? Or maybe I was missing 2 screws, or maybe the screws are the wrong size or something lengthwise. So, big mistake from the television company, but I didn't want to package the TV back up and try to drag it back to Walmart. Okay, so we've talked about a few examples. We got a few practice problems. Okay, so let's go to number 1. Everybody look at that and see if we can write the thread note. Okay, you have that in your notebooks. Let's write it down, and if we get it wrong, we'll make corrections. First of all, what kind of thread is it? Or what kind of hole is it on number 1? Huh? Countersink. Okay, so if you need to look at your example for a countersink, look at your example. Dayton? What do you put for the depth? Oh, yeah, yes, that would be right. You spelled it differently, but that's okay. And that one's drilling all the way. So what would the depth be? All right, we got number 1 done yet? Hunter, you want to try it? Go ahead, come on. Huh? If it's wrong, we'll fix it. You gotta be willing to be wrong. Engineers make mistakes, and we just gotta fix it. That means you're trying. Okay, this is new to everybody, unless you've had some practice looking at hole notes or thread notes for some reason at home. No, you should just go draw the trick. Maybe that one needs a new battery. I don't know. Okay, pretty good effort. Okay, got a couple little details to clean up. Thanks. Good job. Okay, what do we need? What do we need to have? We do, great start, because we have a 1/2 inch diameter. When it goes all the way, how do we write that? We don't use a depth symbol. What do we say? What do we say? Through. And that's spelled T-H-R-U, not T-H-R-O-U-G-H. So that is going all the way through. Okay? Your second line was great. Oh, what is going on? Projector is possessed again. The fan even kind of flickered. The second line is great. He's missing one thing in the second line. What is it? Yeah, the little diameter symbol on your diameter of your 1.0. So everything in the second line, perfect. Except we're just missing that one little symbol. So we got the countersink, 1 inch diameter times 82 degrees. Okay, so again, if you made a mistake, what do? You cross it out and you fix it. Okay, that's what we do. We're also trying to teach engineering notebook standards. Okay, so in here, what are we missing? We're missing the diameter symbol. Okay, good job. Okay, all right. Second one. That one's a little simpler, no pun intended. Right? Oh, Gaspar thought that was funny. Right? Because what type of hole is it? A simple hole. Okay, write your whole note. Someone else gets to go to the board. Hunter, I picked on you last time. You get to pick on someone this time. All right, so everybody write your whole note, and then we'll go over it. Got to have time to process this. I don't think we want a worksheet of 25 whole notes to write and do for homework, do we? So we just got to make sure we get it early and often, and it becomes important when we start using it. We're going to have to figure out what holes we need for our Trammel toy. All right, Hunter, you get to pick on somebody.
Why?
Oh, I'm sure Jason's got it. I don't have any reason not to believe that anybody wouldn't have it. This one's a little easier.
Did you see us pick right there? I was up first.
Yep, that's it. Okay, we have 1/2 inch diameter, 2.5 inch depth. Okay, pretty easy. Now this gets more complicated. We haven't talked about that yet. If you have a simple hole and it's for a peg or something, well then that would be specific. If you have a simple hole, then how close do you want the fit to be if there's supposed to be a bolt going into that hole? Because we have that in this case. We can do it just with measurements, or there are different allowances and sizes based on how sloppy you want the hole to be. Okay, do you want a lot of room for it to slide around and have the bolt go in, or do you want it to be really snug, but still be a clearance hole for a bolt? So we'll talk a little bit more about this. This is just the very introduction. So the last hole, of course, what kind of hole is this? Counter bore. Okay, so let's look at our counter bore example. Did everybody get the simple hole note written correctly? And some of us probably made some beginner mistakes on the countersink. Let's see if we can get the counter bore right. All right, Jace, pick on somebody.
I'm gonna go with Andrew.
Oh, okay, good. He just put his pencil down, so maybe he's got it. Okay, pretty good. We got a couple little mistakes here, I think.
Yeah.
First line, overall diameter, 1/4 inch, depth of 1.75. Perfect. Second line, couple little things. What are we missing in the second line? Kellen?
You have .375 instead of 0.5.
Yeah, we've got, you wrote the wrong number. I don't know what if you didn't look at it all the way or something, but your counterbore depth we have as 0.375. Okay, so this should be 0.375. Okay, and one other little mistake. What else is he missing? Yep.
Radius symbol?
Huh?
The radius.
Yeah, well, the diameter symbol.
Oh,
Yeah, we're missing the diameter symbol here. Okay, so we should have a diameter symbol in here. So I guess if we rewrote that to look perfect, we should be 0.25 with a depth of 1.75 and a counterbore diameter of 0.75 with a depth of 0.375. Okay? All right. Very good. Next, most of you didn't log in to Google Classroom. That's okay. I'll just pull it up here. We'll see how far we get. When is our period over? Oh, we'll get into this a little bit. Go ahead and log in, but I'll go ahead and pull it up. What are we headed into? We're headed into the Trammel project. So I think I posted the full project. And then I also posted the hardware, which we should be able to get started into. So the Trammel toy project is actually in Unit 2, which is assembly design. Okay, so that's one of the things we're going to do. We did some assembly, but we did what was called bottom-up assembly. We built every component in the train and then put it together. Okay, assembly design is getting towards top-down, where you can build the parts in the assembly. So that actually saves a lot of time and a lot of effort and allows us to get it correct a lot faster. So if we look at the Trammel toy project, let's look at the design brief. Okay. And it's taking a minute to load or something here. But what we have, our client, what is a design brief? Last time we looked at a design brief was with the video, right? Well, that's the first time we're kind of introduced to it. Our client is the Do Nothing Toy Company, because that's what a Trammel does. It does a do nothing, right? Target consumer, ages 3+. The designer is Intro to Engineering students. And here's our hypothetical problem. The Do Nothing Toy Company experienced a devastating fire. Unfortunately, all the documentation was lost along with the CAD files. Luckily, I don't know how, but a number of unassembled Trammel toys have been salvaged from the remains. Now, how the plastic didn't melt in the fire, I don't know, but this is the hypothetical situation. What we are kind of doing with this is we're doing the first part of a reverse engineering project. We're going to take measurements and recreate, and sometimes that's all reverse engineering is recreating documentation or analyzing things in detail, figuring out what all the materials are. So that's kind of what we're doing. The point of reverse engineering usually is to do something to make some kind of improvement. It's an improvement to the product, or maybe it's an improvement to the process of manufacturing. Okay, so there is a slight improvement that I found because and this one is very different from the initial one. If we see the initial one that Project Lead the Way came out with, they had a whole bunch of pins and a whole bunch of holes for alignment purposes. Now those are really nice for alignment purposes, and in the real world, that's how things get assembled. You have things that get assembled so it only goes together one way. The other way you could design something is so everything was interchangeable. So it could be assembled, doesn't matter which piece you put in the corner, all four would fit in the corner. Depends on how you want to make your project and what you're trying to do. But by making the corners different, it does allow us to learn some new skills. But those pins are expensive, and 6mm dowel pins are really expensive to find. So I almost gave away an answer that we're trying to come up with. But those dowel pins get more expensive. So this one has about $2.50 in plastic and $2.50 in hardware. So that's getting expensive when you're trying to do things in an education setting. So I modified it a little bit. And when we look at it, you'll see one of the things we changed is first I had an octagon as one of my profiles, and that didn't work too well. Now you still have the octagons, but I already had them printed out before I realized it was a problem. We're going to put a trapezoid in there instead. So what are we going to do? We are going to fully dimension the components. We're going to sketch the parts. And we got to figure out what hardware we're going to need. And eventually, we're going to create a set of working drawings for the Trammel toy. So here's what you'll see. The octagon starts to get to be too round, and you have to be really careful when you tighten it down, or you might have some interference there. So I found out that the trapezoid worked better. So that would be a good design improvement to make that I already sort of made for you. But there's all the components. Okay. So, and this is broken down into steps. First step is Trammel toy hardware and moving parts. But if we look at the hardware, what are we going to do? Quickly sketch multi-views of the dowel pin, the flathead screw, and pan head screw. So we've got 5 minutes. Let's see if we can get a sketch. And I don't know if you'll get to... Now, when I say quickly sketch, I do mean quickly sketch. So we're getting back into multi-view sketches, and we just need to have a sketch that's close. Communicate the idea and get it dimensioned. Okay, so what we want to measure is the length and diameter of the hardware to the nearest 0.01 inches. So I'm going to let you sketch them. Remember, multi-views should line up. So I'm going to let you sketch them, and let's see what your sketches look like. We should be able to sketch all three parts in the next... Oh, yeah. And I'm just going to add a page to this, I guess. Yeah, I'm going to give you a little bit of time to sketch, and then we'll see. We'll see how our sketches look. No, just the hardware. The hardware. Multi-views, not isometrics. The dowel pin, the flathead screw, the pan head screw. Now you have the physical parts, look at them. What's your sketch going to look like? How good does it need to be? There's my dowel pin. That's all we need. Right? Multi-view sketch. I'm done. Is that hard? Huh? What do we need? Communicate the idea. Okay? The sketch does not have to be perfect, but you want to make sure you have all your details. Okay? And then what do our directions say? Our directions say measure using a dial caliper, measure the length and diameter of the hardware to the nearest thousandths of an inch. So we want the length and the diameter. Now, what length and diameter do we want? Okay. On the pin, there's our diameter, and there's our length. On the pan head screw, well, actually both screws, this would be our diameter. Now the pan head and the flat head are different in the way you measure length. Okay? The length on the, and we don't really care about the length of this piece at the top, that's okay. I guess we could, but we also have the plastic because we're going to need this diameter to figure out, how big of a counterboard to drill, right? We're going to need a counterboard in certain places. And the flathead screw, there's a diameter, and the difference with the flathead screw, it's the entire length. That's the official dimension. Now, why is it that way? Where the pan head is just measuring the threads, and they decided the countersink is measuring the whole length? Who decided that? Nancy.
Nancy read it.
Huh?
Nancy read it.
American National Standards Institute. Okay, so we are partway into our first step in our reverse engineering project. We will be moving along just fine. We had our 2-minute warning. So that's the first thing we need to do as our bell ringer tomorrow. We need to get our measurements with our dial calipers. And then we'll see, hopefully we all get the same thing. We should not have as much variation with the calipers on the steel parts as we have with the plastic parts. Because they're all the same and they're all bought at the same time. Awesome. Good job today, guys.
Awesome.